Hey everyone, we talked about the electric potential and the electric potential energy, and now it is time to talk a little bit about the electric potential created by a point charge. We always, when we look at the electric potential, basically we compare it to something else, and that's why we use electric potential difference. Okay, so we never say electric potential. That does not happen. We usually say electric potential difference, and we always compare 2 points within by each other, so that we make one the reference point and the other one we compare it to the reference point. However, there are some mathematical tools that we can get over this problem, and we can find just the electric potential created by a point charge. And let's start this. So assume that we have an electric field that looks like this. Okay, and this electric field, in this electric field, you have 2 points. I'm going to call this point 1, and I'm going to call this point 2. And there's a charge, a test charge, that goes from point 1 to point 2. So we know that W12 is equal to EPE1 minus EPE2, the electric potential energy of 1 minus the electric potential energy of 2. Okay? We also should know and remember that the Coulomb force is equal to K, which is 9 times 10 to the power 9, Q1 times Q2 divided by R squared. Alright, so now we are going just to use the work, because this is work. Now work in general is equal, from what we learned in the past, is equal basically to the force acting on an object times the distance the object travels. Okay? And there is a cosine theta, but we're not going to worry about that because the object and the distance are moving in the same, the force and the distance are pointing in the same direction. Okay, so this is, if we put these together, so let's say like we're like doing an informal way of derivation, because if you want to derive this equation precisely, you have to use calculus, but we do not have calculus here. We have to use algebra and some hand waving, some kind of like quick thing. So alright, so what do? We know that F, the work is equal F times the distance, and the distance we started calling it in this chapter, on the previous chapters, as R. So this is F times R. So work basically is equal F, which is K, Q1 times Q2 divided by R squared, multiplied here by R. R with R goes away. So the energy of between 2 point charges, if you will, the energy of between 2 point charges is equal to K Q1 Q2 divided by R. Okay, and that's a very good equation. I think it's a good idea to put it in a box. We're going to use it later on many times. Okay, so that's this is the energy that is actually required. If you want to define it very well, this is the energy required to keep these two charges within the vicinity of each other at a distance r. All right. So basically, if you put two charges next to each other, they cannot stay next to each other. Either gonna attract each other or they're gonna repel each other. But if you put them next to each other, you will need energy to prevent them from crashing into each other or repelling each other. This energy is equal to this work. Okay? Basically. All right. Now we know from here that charge has moved from 1 to 2. So I can say W1 to 2 is equal to work of 1 minus work of 2. And I can put that here. Work of 1 is equal to K Q1 times Q2 divided by R, but that's R1. Now minus K Q1 times Q2 divided by R, but that's R2 for the second one, okay? Now you can actually take all the common terms out, like K out. Q1 also is common between the two terms, and you are left off with what? 1 over R1 minus 1 over R2. Okay, so that's actually, we just took the common terms out of each term, K, Q1, Q2, right? Now, we learned also that delta V is equal to what? Delta V is equal to minus W12 divided by one of the charges, which we call it like Q0, okay? So we can actually take this here and do that. So K Q1 times Q2 divided by Q0, okay? And since there is a minus sign, so how do we incorporate this into this term? We just say 1 over R2 minus 1 over R1. Okay, so we flip this one here. The negative becomes positive and the positive becomes negative, and we take care of this negative sign. Now this is, remember, this is Q0, this is any charge, okay? So I'm gonna delete with any charge of like that. I said again, this is hand waving, all right? So this charge and this charge are any charge, so it's not like Q1, Q2, or Q0. So I can divide this one by this one, or divide this one by this one, it doesn't matter. And Q2, since it's the only present charge in the equation, you don't have to call it Q2 anymore, you can just call it Q. Okay, so this whole equation, delta V, means that delta V is equal to KQ 1 over R2 minus 1 over R1. And now we can put now the terms together. 1 KQ over R2, we can just multiply this by the inside of the parentheses, minus KQ over R1. So basically, if you look at this term and this term, each term represents the potential, the electric potential for the point charge, but this is on its own. So this is the electric potential for a point charge, this is the electric potential for the same point charge, but at two different spaces, or two different distances, or two different separated areas. And the reason we need that is just because we don't have actually electric potential. We have electric potential difference. Now we can employ math to get over this problem, assuming that this is, where we bring the charge from position number 1 compared maybe to a reference point. We're going to call it the origin. Okay, so this is R1, and here this is R2. Then we have the potential difference basically for this charge when it traveled from R1 to R2 is KQ R2 minus KQ over R1. Now we can bring this charge from a very, very far away place, very far away. Instead of it's R1, R1 becomes so big we can consider it to be infinity. Okay, now if R1 is infinity, what we do, we put infinity here. Now any quantity divided by infinity gets out to be what? 0. And then we end up with this. I'm going to take this here. Delta V, which is equal to V2 minus V1, is equal to this term here only, K Q over R. I don't need to put R2 because it's the only R in the equation. R2, there is no R1. And we know that the potential difference at infinity, or the potential of that point at infinity, is 0. So V2 is no need for it. So basically, we end up with this nice equation. The potential for a point charge is equal to K Q over R, and that's it. This is a very good equation because we are going to use it a lot. So the potential of a point charge at a distance R is equal to K, which is 9 times 10 to the power 9 in free space, times the charge value itself divided by R. Now this is of course a scalar quantity because we derived it from energy here, and energy is a scalar quantity, and that's it. Okay, thank you.